Hello everyone and welcome back to another one of my guides. This one is for science and it's all about the atomic structure, anything about atoms and the periodic table. So these are the topics we'll be covering for today. So let's start with atomic structure. A- Atomic structure is very simple. It just refers to what the atom is made of, and really it's just a nucleus. So there's a bunch of what we call protons and neutrons here inside. It's considered the center of the atom. I'd say it's considered the definitely the center. For me, I call it the center. And it is surrounded by electrons. However, unlike what the drawing suggests, it's actually more of an electron cloud. So these yellow dots, what I'm drawing now, are the electrons. So, like I said, that the electrons are kind of orbiting around this a nucleus here. So all we need to know about an atom is that it's made out of a nucleus with um, electrons, and that's really it. It's that simple. You just need to remember that this is the nucleus, and around the nucleus or around it is the electrons, which is that one. So that's it already. Speaking of protons, neutrons, and electrons, these serve three particular roles. So let's start with the protons. This will now be, what's this one? Subatomic particles. So first is our protons. These are positive charge. And then they also correlate to the atomic number. And this one is also part of the mass number as well. So we'll talk about the mass number later. Meanwhile, the neutrons are just neutral charge. And they also contribute to the mass number as well. How about electrons? Electrons they are negatively charged, and they do not affect the mass number. However, protons and electrons, they do affect the charge. So we'll learn about that charge later. All we need to know is that this charge is important as well as the mass number. So that really is it for subatomic particles. Next is the atomic number and mass number. So how do we find the atomic and mass number? Well, here's the thing. The atomic number is just when you look at the periodic table, there will be a number for each element. I will show you my periodic table in a little bit. Actually, let me just get it real quick. Okay, so here's the sorry for the ad, but here is our periodic table, and these numbers right here are actually, I'll encircle them in red. This is what you call the atomic number. So for helium it's 2, for neon it's 10, so on and so forth. Each element has their own atomic number. Now, to ease the relationship between atomic number and the subatomic particles is that assuming a neutral atom, the atomic number is equal to the amount of protons. So yep, this means that helium has 2 protons, lithium has 3 protons, so on and so forth. Furthermore, how about mass number? Mass number would be the amount of protons plus the amount of neutrons. So how does that work? I'll give some examples right here. Okay, I have some examples here, so we can obviously Just a side note, all of these are neutral atoms, which means protons, amount of protons is equal to the amount of electrons. Let me just write that down here. And from this fact, we can fill in everything here. So let's start with the first one. The atomic number is 35. The name of the element will have to be atomic number 35 on our periodic table. Looking at 35, it's Br, which stands for bromine. Secondly, we are asked to find the amount of protons. And based on our fact that it's assuming neutral atoms, the atomic number is equal to the amount of protons. Therefore, 35 is here, thus the amount of protons is also 35. Next, to find the amount of neutrons, we need to add the mass number is equal to the amount of protons and neutrons. So let's form an equation here. 80, which is our mass number, is equal to amount of protons, which is 35, plus something. And by just subtracting 80 minus 35, you can get 45, which is the neutrons. And since this is a neutral atom, amount of protons is equal to the amount of electrons, hence it's 35. Next, let's do this one. First, it's atomic number 3, which means number 3 stands for lithium. So we put this one as lithium. Then, the mass number. It's not given, however, we know that the atomic number is equal to the amount of protons. Thus, there is 3. And then, now we can get the mass number because we have the amount of protons and neutrons, which is 3 plus 4, which means this is 7. Then, once again, protons equals electrons in this neutral atom, which means 3 protons and 3 electrons. Next one. We don't know the atomic number. However, we can say that the electrons is equal to the amount of protons. So we can put this as 7. Then, we know the amount of protons is equal to the atomic number, which means the atomic number is also 7. Then, from there, we can already identify our element, which is nitrogen. And then finally, we have to solve again for the amount of neutrons. So 14 equals 7 plus something, which if you subtract 14 minus 7 is equal to also 7. Next, number 4. We know that the mass number is 19. And actually, this is... Well, actually, I've double checked it. I thought it was an error, but it wasn't. So we're given the amount of protons, and we know by then protons is equal to the mass, not mass number, atomic number. So once again, we can put 10 over here. Then, to find out the mass number, remember that 19 equals 10 plus something, which in this case is 9. And since protons equals electrons, once again, in a neutral atom, we put it as 10 as well here. Finally, let's name our element, which is 10 for neon over here. Lastly, let's do this one. First, let's base it off our electrons. Electrons equals the amount of protons in a neutral atom. So we have to put 26 over here. Then, we can find that protons is equal to the atomic number, which means it's equal to 26 atomic number. 26 atomic number is Fe, which actually is iron. And finally, we have to solve for the mass number. So just equate this as 56 equals 26 plus blank. And by doing the math, 56 minus 26 equals 30. And there you have it. That is the atomic number and mass number over here. Okay, doing good so far. I make sure to take a screenshot. And we'll move on to the next one. The next topic is the periodic table of elements. So this is the periodic table of elements. There's a lot of ways on how to sort this one. This is the first one. I've sorted them by groups, and I'll show you all my others so far, all my other periodic tables. Okay, so this is my 3 different versions of the periodic table, and this is how it works. The periodic table of elements is 118 elements. It's a table. They have organized it over the years. We'll get into the history a little later, but we can start with the features. So the features, we have two types. So this one is called period. These ones, 1 through 7. Then these ones are called group or family. So these ones are called period. And this one is called a group. So it's important to not mix these up because there might come a place in the test when you have to locate using the period and group. For example, you can use like period 7, group 6. So period 7 would be this one, and then group 6. So it's SG. I forgot what SG is. But it could be used to track elements down, so be aware of that and don't mix them up. Once again, there are 18 groups and 7 periods. Alright. Then there's multiple ways to arrange the periodic table as well. So first, you can use them by their natural state. So as we can see over here, we have the gases in red, the liquids in blue, and the solids in gray, as you can see over here. So most of it is going to be solid, except for exemption would be here mercury. That's the only one that's liquid state, metal in room temperature. Then you could sort it also by metals, non-metals, and metalloids. So as you can see, it's just very much a simplified version of the periodic table. We have the metalloids over here. I think we have to memorize this, so here we go. So this one's boron, silicon, germanium, arsenic, antimony, tellurium, and astatine. So this is basically the border that makes the solids and the metals and the non-metals. Then we have the full complex periodic table from the non-metals to the halogens and noble gases. So all you need to do is just take a look here and make sure you get the gist of it. So we got the non-metals here. This is a non-metal, by the way. So here, then the alkali metals take up most of group 1. Alkali earth metals take all of group 2. The transition metals take all the groups from 3 to 12, sorry. Then post-transition metals are here. They don't really have an assigned group, but they're just all over the place. Metalloids are the one in dark blue. So once again, the ones I mentioned. A continuation of the non-metals here. The halogens over here, which is in period 17. No, sorry, not period 17. Group 17. And finally, the noble gases at group 18. Also worth mentioning are the lanthanides over here and the actinides over here. So that really is most of it. So we're gonna take into the history of the periodic table now. But one thing that I actually forgot to mention is that each time you see a element, you'll have a symbol. So hydrogen, and then this is your atomic number. This would be your name, the name of the element, and this would be a mass number, this one. So yeah, that's how everything is composed. And that's really it for those two topics. So I'm gonna get to the history of the periodic table. All right. Now let's talk about the arrangement of elements in the periodic table as well as the short history. The history began when Hennig Brand, a German amateur and I believe physicist or something, attempted to create a philosopher's stone, which is just another object back then. It's like it makes gold, but he reheated residue from boiled urine, but this actually only led to the discovery of phosphorus. In 1680, Robert Boyle also discovers phosphorus, and he also made this phosphorus public, which phosphorus makes it's made from matches. So that could be where the start of matches began. So by 1809, 47 elements were discovered and patterns started to emerge. But it was only by 1863 that John Newlands divides 56 elements to 11 groups. However, the major breakthrough would be in 1869 when Dmitry Mendeleev started to develop the periodic table using the atomic mass. When spaces were inside the periodic table he created, this actually predicted the discovery of more elements. So we have Hennig Brand, which is a German, and John Newlands, who's English, and Dmitry Mendeleev, who's Russian. So, how is it arranged then? So we can take a look by using the group numbers. So let's start with alkali metals, which is group 1. They exist in other elements, but they are highly reactive, as well as having low density points and melting points. These are the alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. Next is the alkali earth metals. These are still also highly reactive like the alkali metals, but they are harder than alkali metals. They are also shiny, lustrous, conduct heat and electricity, as well as having slightly higher density and boiling points than group 1. These are our alkali earth metals: beryllium, magnesium, calcium, strontium, barium, and radium. Next is the transition metals. These are hard, shiny, and lustrous solids with high conductivity and melting points. They can also take on multiple charge states. These are all of the transition metals. I'm not really gonna name all of them, but they are just transition metals here. By the way, I'm actually a little confused if lithium and actinium, I believe, belong here, or do they belong here? So that's actually a little confusing. Either way, next we have the 4 smaller groups: the boron family called earth metals, the carbon family called tetrals, the nitrogen family called pnictogens, and the oxygen family called chalcogens. These are groups 13, 14, 15, 16 respectively. Next are the halogens. These are group 17. These are highly reactive nonmetals, and they react violently, especially with other metals. They are poor conductors of heat and electricity, and they do have low boiling and melting points. Last but not the least are the noble gases. These are colorless and odorless, but very stable elements. These were called initially inert gases due to the initial no reactions. There was a lack of reactions, hence why this name was formulated, but they're barely reactive. And that's how the periodic table is arranged for the most part, by group. So we can just tick this off the list. Alright, our next topic will be about periodic trends. I'm gonna do 2 at once because they're not the same term, but they basically follow the same trend on the periodic table. First is the atomic radius. This is just the distance from the nucleus to the electron cloud, and it is influenced by the electron configuration. Sorry about that. So basically it can be like nucleus, and then this is the electron cloud, or it could be much closer than that, like this. So that's it for the atomic radius, and that's its definition. Next is the ionic radius. It's basically the size of the ion as an atom gains or loses electrons. It's called an ion because atoms are always neutral. Once they're no longer neutral, they become an ion. So let's say you have a neutral atom, but this is now going to be a negative atom, or this negative ion, and this would be a positive ion. That's just an example. There are two types. There's cations. These are formed when atoms lose electrons and these become smaller. But these are only for metals and metalloids. These are formed from metals and metalloids. So there you go. So gray and blue are your metals and metalloids. Meanwhile, anions are formed when atoms gain electrons and they become larger. These are only for the nonmetals, which are highlighted by red here. I've made this special table because both atomic radius and ionic radius go increases from top to bottom. Which means if you start from the top and work your way all the way to the bottom, as you could see, the circles, which are supposed to represent our atomic and ionic radius, they get larger. However, when going from left to right, they get smaller. So as you could see, let's take a look at period number 4 here. It starts big at potassium, but slowly works its way to be very small by bromine. And I think I see another pattern here that the noble gases are kind of an exemption here. Anyway, in general, it's just increases from top to bottom and decreases from left to right for both atomic and ionic radius. So you can take a screenshot of this one, and we'll move on to the next two trends. Okay, the next two periodic trends are ionization and energy and electronegativity. So ionization energy is the energy required to remove an electron from the outermost shell. So basically, this is your nucleus, right? This would be your nucleus, and you'd have like your atoms. Let's see. So it's basically the energy required to pull out the outermost, like this one here, out of that bond. Hence why we called it, it's also known as it represents how strong an atom outermost electron's bond is. However, there is there's a caveat to this. Okay, wait, this is not here. There, sorry. This applies to noble gases. Sorry. Okay, so yeah, ionization energy is applicable to all elements. However, electronegativity is not applicable to some elements at least. So let me just box that up real quick. There. Okay, so first and foremost for electronegativity, it's the ability of an atom to attract electrons or the tendency to attract electrons. This is obviously important in building compounds because electrons are the bonds, kind of the bonds of atoms here. These are not applicable to most noble gases, as we see in our chart here. As you can see, helium, neon, argon, I believe that's radium. No, this is radon. So these noble gases, as you can see, they don't have any values because I actually don't know the reason, but once again, it's a little complicated, but all we have to know is that there's once again another pattern. It goes from top to bottom. It actually decreases, while left to right, it increases. So it's completely the inverse of the other two periodic trends we studied. So that's really it for periodic trends. Remember just to keep an eye out for the order when you're asked, like is it increasing or decreasing order? Is it from here to here? Make sure to just be careful and you should be good to go. Just remember that these two are inverse, like top to bottom is decreasing and left to right is increasing, vice versa for the other two. All right, we're almost done. We'll just need to study the electronic structure of matter and just a few more topics. All right, the next is atomic theory. It's not listed here, but it is like a prerequisite for electronic structure of matter. So we're gonna see how the atomic structure, like what we thought about the atom, is how did it evolve. So it all started with Democritus, and stated that matter is composed of indivisible particles called atomos, and he himself came up with the atomic theory. Afterwards, an English school teacher named John Dalton stated that all atoms of a certain element are identical, which means all oxygen atoms, all nitrogen atoms, any element of an atom, they're all identical within another. He also stated that each element has different types of atoms. So a hydrogen and helium atom would not have the same atom. Furthermore, combining different atoms results in compounds. And lastly, atoms cannot be divided further. Following that, J.J. Thomson made his Thomson's plum pudding model and stated that atoms can contain a smaller negative particle called electrons. He is an English physicist, and here is his plum pudding model, as we could see over here. However, Ernest Rutherford, a New Zealand scientist, in the new Rutherford's gold foil experiment, stated that positive charge is not pudding, but it's inside the nucleus. So it's not mixed up with the negative, as we could see over here. It's actually inside this nucleus, and the negative is actually over here. He stated also that atoms contain positively charged core, which is once again the nucleus, and surrounded by empty space, which takes up the place of the electrons. Next is Niels Bohr, a Danish physicist, and created the Bohr's orbit model. He also stated that lowest allowable energy is called the ground state, while gaining energy, an atom gaining energy would be considered an excited stage or state. He also stated that smaller orbits exhibited a low energy level, so this one, while the larger orbitals are orbitals considered to be higher energy levels. So these ones contain the highest energy level. Furthermore, these are all stable orbits. But it isn't until we finally get to the most acceptable version of the atom formulated by Werner Heisenberg, a German physicist, and made up the Heisenberg's uncertainty principle. He stated that it is completely impossible to assign fixed path for electrons, because it's also impossible to measure something without disturbance. If we wanted to observe an electron, it creates uncertainty in its position and motion. And that's really it for atomic theory, really. It's just these 6 people. So, Democritus, John Dalton, J.J. Thomson, Ernest Rutherford, Niels Bohr, and Werner Heisenberg. So feel free to screenshot along with periodic trends, and we'll move on to the actual proper of electronic structure of matter. Next is the quantum mechanical model of an atom. It finds the probable location of an electron in an atom. To do this, we need to find the energy level, sublevel, or subshell, and the orbitals. First is the energy level. It's a fixed amount of energy that an electron can absorb, and follows the Aufbau principle, which states that lower energy levels must be filled before higher ones. Here are the first three levels, with 2 electrons, 8 electrons, and 18 electrons respectively. So I'm going to give you a visual representation of what is the Aufbau principle. Wait. Suppose that this yellow dot here would be, blue. Suppose that this blue dot here would be your nucleus. And then let's draw a ring around it as our first energy level, and use yellow dots to make sure that to represent our electrons. So this is our first energy level, and it can only contain 2 electrons maximum. Now, it looks good so far. Now let's draw the second energy level, and it can contain up to 8 atoms. 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. Now, Aufbau's principle states that lower energy levels must be filled before higher ones, which means, as you could see, this first energy level here only has one electron. So we can't do something like this because the first energy level does not have the maximum amount of electrons first. So we have to do this first, and only then we can start filling the second energy level. Another thing to note is the valence, which is just the amount of electrons in the outermost energy level. It is using this formula right here. Not really formula, but just study the table. Basically, you just count left to right using the groups, but you have to skip the transition metals. Next is a sublevel or subshell. Each energy level has a sublevel, and it can either be S, P, D, or F. And as you could see from my periodic table here, this is what we know called the S block. This is what we call the D block. This is what we call the P block, and this is what we call the F block. So it just basically states the orientation. So S has only like one orientation, P has 3 orientations, D has 5, and F has 7. Orbitals are regions in space calculated to have electrons. Electrons in a particular subshell may be distributed among volumes of space of equal energies called orbitals. And remember Pauli's exclusion principle, 2 electrons max per orbital. And well, the amount of orbitals, as you could see over here, is the same as the amount of configurations each type of atom has. So S type of shape of atom has 1 s orbital and 1 configuration. P contains 3 configurations and 3 p orbitals, and so on and so forth. This would be pretty important, and locating elements should be pretty important in our last topic here, which is called the electronic configuration. And yeah, we're on to our last topic. We're almost there. So yeah, let's keep going. Alright, so the final topic would be electronic configuration. I've already did a little bit of setup here for how to discuss it. So let's start. We're going to first do step 1. Let's determine what atomic number is helium. So He. We want to find He over here, and we find it to be on this side right here. So it's a bit blurry, but that is number 2. So we know the atomic number is 2. Next, how do we know an energy level? Well, these numbers from 1 to 7 called periods are actually indicative of their energy level. This is also their energy level. So these 2 elements over here are in the first energy level. These ones are at the second. These ones are at the third, and so on and so forth. So the period is the energy level as well. But make sure to count the ones above it. But since this is in the first energy level, it's obviously only going to be first energy level. For now, it's 1. Next, what are the sublevels? The sublevels are once again the S, P, D, and F. And once again, let's see. So we pass by 1s over here to hydrogen, and then we already arrive at helium still at 1s. So that's just S. Number of orbitals. So we need to count how many different 1s, 2s, 3s, how many different orbitals we pass by. So once again, 1s still at hydrogen, and once again, already at helium, we're still at 1s. So it's just going to be 1 orbital, which is 1s. Now, how do we do this? So this is already we already did steps 1 and 2. How about what's the superscript? Well, first and foremost, let's start off with the only one, which is 1s. 1s, okay? Now, we want to count how many elements we passed by to get to helium under 1s. So there's 1 for hydrogen and 2 for helium. So since we passed by 2 elements covering the 1s, that means we covered 2. And that's already the electronic configuration of helium. Very simple. Just reminder that the exponent or the what says superscript is the max superscript for S is 2. The max for P is 6, sorry. The max for D is 10 and the max for F is 14. But we'll not really need F because the cutoff point is at xenon. So we're not going to touch F. But it's also important to know. Now let's start with a slightly more complex one, but still pretty easy. Let's try neon. Alright, so neon's atomic number, once again, we're gonna find Ne, and it's, oh sorry, I didn't label it, but Ne. And it's neon, and it's right over there at number 10. So atomic number is 10. Now, what are the energy levels associated with neon? So it's in the second period, second period, as you can see over here, second period. But it's also above the first period. So since it's second, it also means it's first. So it's the first and second levels. So to put things for simply, the energy level is the period number and the numbers before it. So it's energy levels 1 and 2. Sublevels. So let's do the same thing again. So we pass by a letter S. So hydrogen, helium. Then we pass by 2s, to lithium and beryllium. Then we encounter a new letter, 2p. And that means the sublevels are S and P. Then we want to check the number of orbitals. So once again, let's pay more detail now. 1s for H and helium, 2s for lithium and beryllium, and then finally 2p for boron all the way to neon. That means we passed by 1s, 2s, and 2p. Now, let's count how many of each one. By the way, you should apply this maximum number automatically up until the last orbital you listed. So immediately, 1s2, 2s2, but we're not sure about 2p. And then it's only then you start counting. So 1, 2, 3, 4, 5, 6. 6. So that means it's 2p, 6. Fairly simple. So it gets a little bit more complex. So let's now try something from the third period. Let me just clean this up. Let's try something from the third period. How about let's try sulfur. Let's try sulfur. Is that how you spell sulfur? I don't know, but sulfur is S on the periodic table. So we want to find S, and once again, it's 16. Yeah, 16. Next is the energy level. So it's on period 3, which means it's also in energy levels 1, 2, and of course 3. Next is the sublevels. So let's try this again. We're just gonna focus on the letters, not the numbers for now. So we pass by 1s, 2s, 2p, 3s, and 3p. Good. We pass by S and P just once again. Number of orbitals. Now, let's count to the different orbitals we pass by. So, hydrogen to helium for 1s, that is 1 orbital. Then 2s for these two, that's 2 orbitals. 2p for these elements, that's 3 orbitals. 3s for these 2 elements once again, that's 4 orbitals. And lastly, all the way up until sulfur, 5 orbitals. So that's 1s, 2s, 2p, I believe, yep. Then 3s and 3p for a total of 5 orbitals. Now, once again, we're going to apply the same rule as last time. Up until the last orbital you've listed, just put the max number. So 1s2, 2s2, 2p2, 3s6 because it's an sorry 2p6, my bad, 2p6 because p is maximum 6, then 3s2. Then immediately jump to the 3p section and count how many elements you had to go through before you reach sulfur. Yeah, so that's 1 2 3 4. That means it's 3p4. And yep, that's going to be our electronic configuration for sulfur. Now, let's do one last example. This one we'll have to deploy a new tactic because the amount of orbitals is so high that the configuration will just get too long for us to list. I'll choose bromine. So bromine is located over here at 35, and it's in the 4th energy level, which means it's also 3rd, 2nd, and 1st. I mean 4th period, but it occupies all of these energy levels. So the energy levels are, the bromine atomic number first is 35, then occupies energy levels 1, 2, 3, and 4. Now, sublevels. Let's do this again. This one's S, S, P, S, P, S, D, and finally we arrive at bromine at P again. So we did pass by S, P, and D. Now, number of orbitals. This is gonna get tricky. So, I'm not gonna say them all out anymore but oh well. Anyway, so 1s for these two, that makes 1. 2s, 2p, 3s, 3p, 4s, 3d, and finally 4p. Alright, so once again, 1s, 2s, 2p, then 3s, 3p, 3d, 4s first, 4s, 3d, and 4p. And that is a grand total of 8 orbitals. Now, let's try to list it down our traditional way. So it's going to be 1s2. Remember, just give the maximum number per orbital up until the last one. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p. Let's count how many elements we have to pass through. 1, 2, 3, 4, 5. So 5. Now, this is the acceptable electronic configuration, but we can shorten it using the noble gases. So the nearest noble gases before this, the previous noble gas before bromine, is argon, not krypton, because we haven't passed by it. It's argon. Argon has an atomic number of 18. So we want to sum up these numbers in the exponents until they match 18. So 2 plus 2 is 4, 4 plus 6 is 10, 10 plus 2 is 12, and 12 plus 6 is 18. So we can actually just cross out all of this and just put these brackets A, R, then just copy the rest. 4s2, 3d10, and 4p5. And there you have it. I gave an example for all of it, including how to shorten it with using the noble gases. And with that, I just need to clarify a few things. If you're asked a question, let's ignore this for now, the stroke, my bad. But if you're asked a question, how many electrons are in the 2nd energy level, you just have to rely on the numerical coefficient. So that's just 2s and 2p. Then sum up the exponents. That's 2 plus 6, and the answer is 8. If you're asked, what's the total amount of electrons in a certain sublevel, like let's say how many total electrons under the S sublevel, so highlight everything in S, and once again tally the sum. So in this case, it's once again 8. Then once you're asked the mix of both, how many electrons are there under the second energy level and P sublevel? So second energy level and P sublevel, which means it's this. So the answer is 6. So in conclusion, if they're asking for how many electrons in an energy level, rely on the numerical coefficient. If they're asking for how many electrons in a sub-level, rely on sub-level, or the letters here. If they're asking how many electrons on a mix of the energy level and sub-level, combine both two concepts. And with that, that is the entirety of this review. Thank you if you made it all the way to the end. I tried to get this done yesterday, but there were just so many topics to do and a lot of other projects that I couldn't get it done in time. But hey, at least I got it done. Once again, thank you so much for watching, and I hope this helps. Good luck on your test. Take care of yourselves, and I'll see you guys in the next one. Bye-bye.